So for day 5 of chapter 11, we are going to begin to talk about our third and final conic of this chapter that we're going to discuss, and that is a hyperbola. So the way we're going to approach talking about a hyperbola is looking at the shape of the graph, identifying some of the major parts of it, and connecting the structure of the equation of a hyperbola to that of an ellipse. The equations of a hyperbola and ellipse are pretty similar, and they share some of the same vocabulary words. We'll talk about the similarities and differences in general, and we'll start first by looking at the shape here. So here, those two blue arcs would look to be kind of parabola shapes. Both of them together make up a hyperbola. So if you look at the graph of a hyperbola, there's a couple things that vocabulary words that should look familiar, and that is a hyperbola has two foci, much like an ellipse has two foci. A hyperbola also has a center, like an ellipse, and also has two vertices, like an ellipse. The major difference, though, however, is instead of a hyperbola being, an oval shape or an ellipse, where the foci are in between the center and the vertex, and it makes kind of an oval shape. In this case, we have two what look to be parabola shapes going in opposite directions, where the focus is further away from the center than the vertex. And we'll talk about how to find the length or the value to get to the focus and how that's slightly different than an ellipse. But in general, a hyperbola will have two foci, it will have two vertices, it will have a center, much like an ellipse does. So again, this, like I said, the focus is what I would say outside of the vertex from the center in a hyperbola, whereas it wasn't so in an ellipse. So the way we're going to look at this is if we look at the equation, and we're going to try and identify some of the parts of it like we would an ellipse, and then talk about how the structure of the graph will be slightly different. So the major difference in the equation of hyperbola versus an ellipse is there's a subtraction sign between our variable terms rather than an addition sign. So that is the key difference in what the equations look like. We'll find the center the same way as we did with an ellipse. So in this case, the center for a is 0, 0, because it's just x squared and y squared in the numerator. And then what we need to identify next is our a and b value, and we'll talk about how those are going to impact the graph of the hyperbola here in a second. So in this case, we want to identify a, and your instincts might say at this point, well, a is probably 4, which would be the square root of 16, because in an ellipse, a was always came from the larger of the two denominators. But the reason that was that way is because the equation was x squared over something plus y squared over something. And because the order of addition doesn't matter, it's commutative, I could exchange which variable I wrote first, so we needed a way to definitely identify the a value, which is the in an ellipse, the distance to the vertex, and told us where our foci are going to be. So a was key for us to identify. A is going to be very important for us to identify in a hyperbola, but a is not the larger of the two denominators. It doesn't come from the larger of the two. It actually comes from the denominator that's first. So in this case, 9 is first in terms of the denominator, or our x term is first with 9 in the denominator, which means a is going to be 3. And in a hyperbola, a will always come from whatever denominator is written first. Not the larger one, but first, because the order of subtraction matters. So if it's x squared over 9 minus y squared over 16, that will be a different graph than if I were to flip the order of those two variables. So a is 3 and b is 4. Now, like an ellipse, we could put that stuff on a graph. So put my center at 0, 0, and if a is 3, and where 3 is underneath my x variable, I should go 3 units to the right and left of center, and b is 4, so I should go 4 units above and below center. So right here, we would, if this were an ellipse, we would draw our oval shape that connects those points. The difference here is, like we talked about, the shape of this graph is different. We have two parabola shapes going in opposite directions, and they are at two vertices. So the way we figure out the direction that this is going to go will come from whatever variable is written first. But to make sure that we accurately sketch this graph, we're going to draw a couple things that aren't technically part of the actual hyperbola, but are very good tools for us to graph this as accurately as possible. The first one would be, once we have our a's and b values graphed, we can connect them with this dotted box. And again, the dotted box is not part of the hyperbola graph, but will be very, very helpful in identifying some of the properties and locations of what this graph looks like. So I'm going to draw that dotted box there, and then when I think about it, I need to kind of understand which direction this hyperbola is going to go. So we have two parabola shapes going in opposite directions. That could either be going up and down or left and right. And the way you identify that is whatever variable is written first. In this case, x is first. So these two endpoints on the edges of my box will be my vertices, and my hyperbola will open left and right. So, and that's again because x is written first. But then, how do we know how wide to make these parabola shapes on either side? And I can just kind of draw this parabola shape off those vertices that I colored in orange, but it wouldn't necessarily be very accurate. One thing that hyperbolas have are asymptotes, and the asymptotes are, lines that act as boundaries for a function, and in this case our asymptotes are going to be diagonal. So the quickest and easiest way to draw these asymptotes is using this box that we drew. So the asymptotes will always go through the center and actually through the corners of our box. So we can draw two diagonal lines going each direction through the center and through the edges of our box. And again, the box is there as a reference, but the location and direction of the asymptotes really have to do with our a and b value. But instead of complicating it, trying to memorize, which way to go, how to count the line, the box is a really helpful tool, because if you draw the box correctly, then your asymptotes will be in the right place automatically. So we draw these as dotted lines because they're going to act as boundaries for our hyperbola. So we technically have enough to draw kind of a rough sketch here. So because this is going to open left and right, the vertex would be at the edge of the box there, and it's going to look something like this. So this is technically the shape of our hyperbola. And again, we knew that it opened left and right because our x variable is written first. The last thing about a hyperbola that we haven't identified, or about this one we haven't identified, are where the foci are. And again, we talked about the shape a little bit ago, and the foci are going to be further away from the center than the vertex, but in line with the vertex. So we need to find our c value. So the way we find our c value in hyperbola is actually the Pythagorean theorem, as it is. C squared equals a squared plus b squared, which is slightly different than the way we found it with an ellipse. So then if I put my a and b values squared in the appropriate place, I should get c equals 5. So what that would mean is I need to go 5 units away from the center in the x direction, because that's the variable that's written first, and that's the direction my hyperbola opens. So I should plot my two foci 5 units away left and right, and that would be the graph of this hyperbola. And for b, we're going to walk through the process again. The difference here is our center is not at 0, 0, and we can tell that from the numerators of our fractions on the left side of our equation, much like we did for an ellipse. So the first thing I'm going to do is identify my center, which would be -1, +1. And then I'm going to identify a and b so that I can begin to put this graph together. So a is always going to come from the denominator that's written first, and in this case 25 is the denominator that's first. It just happens to be the larger one. If you look back at the previous example, 16 was the larger denominator, but it wasn't where our a value came from. So in this case, because 25 is first, that's our a value, and then b would be the square root of 4, which is 2. And then I could put this on a graph. So plot my center, and then to know how to draw this reference box, I'm going to go 5 units, in this case above and below my center, because my y variable is written first, and then 2 would be to the left and right of center, because that comes from the denominator of our x variable. So if I draw my box here, that's going to be a kind of a guide to know where to graph this hyperbola. So this hyperbola, we should maybe at this point be comfortable saying is going to open up and down because our y variable was first, which tells me that my vertices are actually at the top and bottom of my box. The next thing I want to draw I'm going to draw in my asymptotes because I want to make sure that I'm accurate in terms of where to sketch this hyperbola, and without the asymptotes we'd basically just be guessing. And one thing I do want to point out about the asymptotes, you notice in the previous graph, I didn't necessarily just like follow the line with my graph. I want to make it U-shaped, but I want to make it kind of point going out and towards the asymptotes, but it's not going to, it's not going to hug them very tightly, at least not at the beginning. Eventually, as the graph, if I were to kind of zoom out, you'd see it get closer and closer to those asymptotes, but they're not going to get there right away. We should probably draw them more like parabolas, but if to the best of our ability, show that they're going to kind of go out and up at the same time. And you'll see kind of how I do that here for B. So again, I'm going to draw my asymptotes in. They'll always go from the center through the corners of the box. So I have two asymptotes, one going each direction. Should look something like this. And again, because the y variable is written first in my equation, this hyperbola is going to open up and down. So I've already highlighted my vertices in green, so I could sketch my hyperbola, and that would be technically all of the graph. Just those two U-shaped parts are the only parts that are actually the graph. Now the next thing I want to do, make sure I find is my foci, and I want to plot those. So I'd use c squared equals a squared plus b squared. So a squared is 25 and b squared is 4. So c should be the square root of 29. And the square root of 29 is slightly more than 5, but less than 6. So if I plotted those points, again, they would be in line with my vertex and in line with my center. So in this case, I'd be above and below my vertex. So I should plot those points, and I'm just going to label them with a small f to show that those are my foci. So that's kind of a general process for graphing hyperbolas. We'll get a little bit more in detail in terms of what the equations of the asymptotes are, because we do want to make sure we identify those correctly, but the equation looks very similar to an ellipse, so we're going to write the standard equations for a hyperbola, and there's technically two, because again, like I said before, the order in which the variables are written, either x first or y first, affects the direction of the graph, so we want to write them as two separate equations because they technically are different. So the first one would be, if I write x first, I would write x minus h quantity squared over a squared minus y minus k quantity squared over b squared equals 1. So very similar to our ellipse standard equation, only the difference is there's a minus between there rather than a plus. And then the other one would be if I wrote y first. So I'd get y minus k quantity squared over a squared minus x minus h quantity squared over b squared. And again, I want to point out that a is in the denominator of whatever variable is first. So in the first equation I wrote, a squared was underneath x because it was first, and in the second one, a squared is underneath y because it was written first. So in these general equations, our centers would be hk, and then we want to talk about the direction. So if x is written first, it's going to open left and right, much like example 1a, and if the y variable is written first, it's going to open up and down. So there are two pieces, one opening up, one opening down. And then we already talked about the foci. The way we'd find them is by using the actual Pythagorean theorem, c squared equals a squared plus b squared, and again, c would be the distance from the center to the foci. So whatever number we get for c, we have to pay attention to what direction we should count that to, because it should be in line with the vertex and in line with the center. And then the only other thing we have to talk about in terms of notation would be actually the equations of the asymptotes, because the equation of them, it's a line, so we need a slope and a point to write an equation. We want to be specific about those because they are very specific lines that are boundaries for my hyperbola. And the equation for our asymptotes is going to be y equals plus or minus m times x minus h plus k. And all that really is us using our center point. You'll see that x minus h looks very familiar in terms of our center, plus k, and then m would be the slope of the line, and I'll show you how to find that. So Again, h and k come directly from our center. And then in terms of me finding the slope of the line, that box is going to be key to do that. So if I go back to example 1a, walk through the asymptote, writing the asymptote process here. So if I want to write the equation of the line, the first thing I should do is calculate the slope. So I go from the center to the corner of the box, and I just count rise over run. So in this case, the slope would be plus or minus 4/3. And the reason why it's plus or minus 4/3 is if I go from the center and I go up 4, right 3, that puts me on one of my asymptotes. And then if I go back to the center and go up 4, left 3, that puts me on my other asymptote. So the slope of my asymptotes are technically two lines, and one is a positive slope of 4/3, one is a negative slope of 4/3. So if I wanted to write my equation, it'd be y equals plus or minus 4/3 times the quantity x minus, and then 0 is the x coordinate of the center, plus 0, which is the y coordinate of the center. So if I wanted to, I could just write this as y equals plus or minus 4/3 x. And that would be the equation, or that would be the equations of my two asymptotes. And then for b, I want to also identify the asymptotes. The difference here is the center is not at 0, 0, so we will have those coordinates reflected in our equation. So first thing I'm going to do is find the slope. So the slope would be, if I go from center up and over to the corner of my box, that would be up 5, right 2, or I could go down 5, left, or down 5, left 2, down 5, right 2. As long as I go from the center to a corner and count my slope correctly, I should get two slopes, positive and negative 5/2. So then if I wanted to write my equation, it would be y equals, I should say y equals plus or minus 5/2 times the quantity x, and then it's technically minus negative 1, that's the x coordinate of the center, so plus 1, so that's x plus 1, and then the plus 1 on the outside comes from the y coordinate of the center. So that would be the equation of my two asymptotes. And that's kind of the process and how we're going to identify them. Using the box that we draw will be super helpful in finding the slope of the asymptotes and also the location of them. So we're going to look at our next example here, and we are given the equation of a hyperbola 4x squared minus 9y squared equals 36. And I know it's a hyperbola in this case because I have a subtraction sign between my x and y variable. So the first thing I want to do is actually write this in standard form. So I'd have to divide everything by 36, which would give me the equation x squared over 9 minus y squared over 4 equals 1. So here's my standard form equation of the hyperbola. So I should first identify my center, and my center in this case is going to be 0, 0. And then I want to identify a and b so that I can draw my box and then begin putting this graph together. So a, again, is always going to come from the denominator of the variable that's written first. So in this case, a would be 3, and b would be 2. So I'm going to put that together on my graph. So I'm going to graph my center at 0, 0, and then here's how I'm going to draw my box. I'm going to go 3 units to the right and left of center, and the reason why I'm going to go 3 units left and right is because a is underneath my x variable, so that tells me I'm going to count 3 units right and left. And then I'm going to go 2 units up and down of center, and that comes from my y variable, and so I'd count that in the y direction. And then I'm going to draw my box here. So here's my reference to what this hyperbola is going to look like. So the next thing I want to think about is, what direction is this hyperbola going to open? Is it going to be open? Is it going to open left and right, or up and down? And because my x variable is written first, it's going to open left and right. So what that tells me is the endpoints at the edge of my boxes, left and right of center, should also be my vertices, because again, that's where my hyperbola is going to touch and open to the right and to the left using that box. So I can identify those vertices, even maybe before I graph the actual hyperbola. And if you wanted to, you could find the asymptotes and sketch the whole thing and then identify the information, but I like to kind of go as I put the graph together. So there are my vertices, there's my center, and then I can find the c value before I even finish the graph. So c squared is going to be a squared plus b squared, so then c squared is going to be 9 plus 4, which would give me a c value of the square root of 13. So again, square root of 13 is not a perfect square, but it is between two perfect squares. So the square root of 16 is 4, and the square root of 9 is 3. So square root of 13 should be somewhere between 3 and 4. So I can plot my foci, and again, square root of 13 is the distance from the center to the focus, and it should be in line with my vertices and in line with my center. So I'm going to go root 13 units to the right and root 13 units to the left, somewhere between 3 and 4. So the coordinates of my two foci would be negative root 13, 0, and positive root 13, 0. Or if you wanted to, you can call it plus or minus root 13, comma, 0. And then before I draw my actual hyperbolas, I do want to make sure I sketch my asymptotes so that I can be as accurate as possible. So I'm going to sketch them. Again, they go from the center through the corners of the box. So there's one here, and then maybe one going the other direction. And try and be careful that you're, following at the same slope. Try and make it as linear as possible, obviously, because that will help me keep my shape of my hyperbola straight. So there are my asymptotes. So I can actually sketch my graph here. It's going to open right and left and have the vertex there at the edge of the box, so it'll look something like that. And all the pieces of the graph are on there. I just want to identify the equation of the asymptotes. So what I'm going to do is calculate the slope. So again, from the center to the edge, or to the corner rather, I'm going to get a slope of up to the right 3, or up to the left 3 if I go to my other asymptote. So my slope should be plus or minus 2/3. And then if I want to put my equation together, it'd be y equals my slope, which is plus or minus 2/3, times the quantity, x minus the x coordinate of my center, which is 0, plus the y coordinate of my center, which is 0. And you can leave it like that. If you want to get in the habit of writing that, even when it's 0, 0, that's fine. But that can be written slightly differently, because x minus 0 is x, plus 0 is still x. So I can actually just call this y equals plus or minus 2/3 x. And that would be the graph and all the information of this hyperbola. And for the last example, we are going to walk through the process again. Here's my equation, x squared over 36 minus y squared over 9 equals 1, and we want to graph and identify all this information for this hyperbola. So the center is the first thing I like to identify, and this in this case would be 0, 0. And then I'm going to use my equation to identify my a and b value. So a is going to be 6, and b is going to be 3. A will come from the denominator that's written first, underneath the variable, in this case, which is x. So then that should tell me, if I graph my center 0, 0, I should count 6 units to the right and left of the center, and 3 units up and down of the center. And again, I go 6 right and left because that 36 was underneath my x variable, so I go left and right of center in the x direction, and 3 above and below because 9 is underneath the y variable. So then, what direction is this hyperbola going to open? And because x is written first in my equation, it's going to open left and right. So what that tells me is those endpoints on the box that I highlighted there in green are my vertices. So I could actually probably say the coordinates of the vertices, and those would be negative 6, 0, positive 6, 0. And then I could actually identify my c value, so I can know where my foci are going to be. So c squared is going to be a squared plus b squared, and a squared is 36, and b squared is 9. So if I add those together, I get 45, so c is going to be the square root of 45. So the square root of 45 is not a perfect square, so it's not a whole number, but it should be somewhere between 6 and 7. Because 6 squared is 36 and 7 squared is 49. So I should plot my points somewhere between 6 and 7 units away from the center in the same direction as my vertices. So I'm going to plot my foci here. It should be outside my vertices there. And then before I can sketch the actual shape, first I'm going to write my coordinates for my foci. And because the x and y coordinate in the center is 0, 0, I can just say plus or minus root 45, comma 0, or you can write them as 2 separate points. And then, before I finish sketching this, like I said, I'm going to draw my asymptotes in. So I have asymptotes that go through the center and the edges, or corners of the box. And then if I want to write the equation in the asymptote, I will identify the slope and consider the point. But I could actually sketch this. So it should open left and right and be bounded by those asymptotes. So my graph looks like that. And then for the equation in the asymptote, I'm first going to find the slope. And the slope is going to be plus or minus 3/6, or I can call it plus or minus 1/2. That's again from the center. If I go up 3, right 6, that reduces to 1/2. So I have my slope, and then to write my equation, it's going to be y equals plus or minus 1/2 times the quantity x minus 0 plus 0. But because we're centered at 0, 0, I can just say y equals plus or minus 1/2 x. So that's really the process for now in terms of graphing a hyperbola. We will talk a little bit more about coming up with an equation for a hyperbola based on some information, much like we did with our other conics. But if you can identify your center and A and B and draw your box accurately, you should have a real good reference on how to graph these hyperbolas. Just be sure that you're considering what direction the hyperbola is going to open very early on in the problem, so that you don't plot your vertices and foci and write your asymptotes potentially incorrectly.